All right. So there we go. We're now recording, and we can pick up from where we left off yesterday. So welcome. I am home today. I'm in my office at home. I'm not at school today. So yeah, maybe it's a little bit quieter. I know some of my colleagues were walking around and perhaps being a little bit loud, so I decided to film from home today. We left off yesterday talking about, well, introducing projectile motion, which is effectively two-dimensional kinematics. So just to recap kinematics, it is the study of trajectory. We're not trying to analyze what causes the motion. We're trying to analyze, assuming the motion already exists, where is it going to go? Is it linear? Is it parabolic? You know, stuff like that. And we also talked yesterday in great detail that we assume that we're starting from acceleration. Acceleration is where it all begins. Because if you assumed that we had the displacement equation, we're done. You know, trajectory is a study of displacement as a function of time, d of t. So if we assume we have d of t, we're done. So that there's really not a whole lot to study, assuming we start with displacement. So acceleration is not only very easy to measure, you can obtain acceleration mathematically by studying forces, which we'll do in the next chapter. So we assume that we start with this sort of acceleration idea, and then we can actually analyze the corresponding motion. Now, yesterday I also showed you how to derive the one-dimensional kinematics equations using a little bit of calculus. You can integrate twice. Now, I will remind you guys that we don't necessarily have to do any integrating in this class because it is an algebraic-based physics course. So I'll never test you per se on solving a differential equation or deriving the equations of motion, because that involves calculus, and I think that involves details that I don't think are really within the scope of this course. But I presented them to you hopefully to help you draw some connections between where these equations come from. I can sympathize with being in undergrad and just being shown equations on the board. And, you know, I feel like the equations are just kind of coming at me. And I'm left wondering, you know, where did this come from? Why is this useful? When is this true? When is this not true? And it was hard to approach questions that way because I had no context for these equations. So, you know, these lectures are supposed to help present, you know, the background and you know, really get your brains thinking, where do these equations come from? And, you know, the homework and the tutorials are really where you get your hands dirty with the practice. I will try to make some lecture time to do some worked examples, but, you know, of course, that's the lecture time is not the appropriate format per se to do example after example after example. That's what the tutorials are for. So moving on, with two-dimensional motion, we understand that 1D wasn't all that useful in the real world. I mean, although there are some problems that study one-dimensional motion in the real world, most of the real world is in 3 dimensions, right? So 1 dimension is not all that helpful. So we need to sort of work our way up to broadening this analysis from 1 dimension into, you know, set the 2 dimensions and eventually 3 dimensions. Now, a little bit of spoiler, 3-dimension is just exactly the same as 2-dimensional analysis. So this class will only outline how to do 2-dimensional problems, because if you happen to have a 3-dimensional problem, you just add a z direction in addition to your x and your y. So it's really not all that different. So anyway, here's where we left off. We were talking about coordinate systems. And I alluded to yesterday, and I think it was part of the pre-class yesterday as well, when you're studying 2-dimensional motion, what do you have to do differently, if anything? And that idea, I've received a few emails about this, so I'll try to clarify as best as I can. What I was alluding to is, you know, 1-dimensional problems inherently are easier, not necessarily easy, but easier because it's 1 dimension, right? So those equations we derived were relatively easy to use, and, you know, there's only 4 of them. I guess there's technically 5, but we don't really use the 5th one. And I was trying to say, if we go to 2 dimensions, do we kind of have to just throw all of that out and start from scratch because 2 dimensions are just so much more complicated? Or can we take what we learned from one dimension, and can we somehow use that as a framework and build upon it and, you know, use it for two dimensions? So that's kind of what I was alluding to. And the answer is, with minimal searching, I think you guys would have been able to find this, is absolutely we can use our analysis we've developed for one-dimensional motion. Absolutely we can. There's just one very, very small caveat, and really it boils down to coordinate systems is what I was trying to introduce yesterday in the last few minutes of lecture. So in two dimensions, you need to now know how, you need to have a notion of, you know, how to represent each direction, whether it be X and Y, or, you know, some other type of coordinate system. And this analysis, you can build upon the one-dimensional motion very easily, assuming your coordinate system has 90-degree angles to one another. And that's what we would call independence. So we didn't have enough time yesterday to go through this, so we're going to take a little bit of time now to go through it. Let me just show you a little bit about what I mean about coordinate systems. And I will start off with coordinate systems by saying they're a mathematical invented construct. Nature does not know coordinate systems exist. If I were to, you know, throw a ball, the ball will go wherever the ball is going to go. You know, nature does not know how humans have chosen to mathematically represent this motion. So it doesn't really matter what coordinate system we pick. We should all get the right answer as long as we do the math correctly. So here's an example of what I mean. If we look down now at the screen, example 2 in the typed lecture notes talks about representing the acceleration vector of a box in its components. And you can only really talk about the components of a vector once you've established a coordinate system. So here they say, or I guess I say, to represent the coordinate system as a standard XY Cartesian coordinate, and then repeat the same analysis, but using a different coordinate system. And the coordinate system, the second coordinate system I want you guys to do is a rotated coordinate system. And that may not be clear of what I mean at the moment, but it's okay, I'll walk you through it. So a standard XY coordinate system, let's do that for the first one. I'm just gonna write here my coordinate system in green. And if this box is sitting on a ramp, the acceleration is inherently in this direction here, a vector right down the ramp. So assuming I've chosen a coordinate system of x comma y, you know, the standard coordinate system, then I want to represent this a vector in terms of its components. So the components in this case are going to be a sub x and a sub y. Right, how much of this vector is pointing in the x direction and how much of this vector is pointing in the y direction? Well, looking at this here, we know the incline has a bit of an angle associated with it. Now, we're not told what that angle is in person, so let's just represent this just by an arbitrary value, theta. And we know the acceleration is down the ramp. So how does theta, with respect to the ramp, where does that come into play with regard to our coordinate system? So you might recall from, I believe in Ontario, they teach this in grade 9 math, so it would have been a long time ago for a lot of you, but hopefully you remember this pattern. There's something in geometry called the Z pattern. So it tells you that this angle down here, the theta that I've drawn, using the Z pattern, we know it's going to be the same theta as over there. So now I've been able to tie in a physical quantity that I can actually measure in real life. I can measure the angle of a hill quite easily. And I can tie that into figuring out kind of what angle the acceleration vector is pointing in relative to the horizontal, relative to the x direction. So now I can actually easily break down my x direction and my y direction. So the x direction's acceleration is going to be a cos theta, and my y direction is going to be minus a sine theta. And if I had to draw those vectors for you, that would be this right here, AX, and then AY is negative because it points downwards. Now, again, if we're inventing a coordinate system, maybe you want to make the downward direction positive for, you know, your own convenience. That's fine. If we're inventing a coordinate system anyway, you can make whatever direction positive you want. Inherently, I like to make down negative and up positive because for me, that just seems more natural, but you can do whatever you want as long as you are mathematically consistent through your whole analysis. So here, I would say, is the answer for the first part. Break down, the question being break down the acceleration into its components using x comma y. That's the answer, a cos theta, negative a sine theta. Now, the second part of this question was to change the coordinate system to a rotated coordinate system. So if I rotate my coordinate system, one of my directions, now this isn't the traditional x direction anymore, right? There's nothing that's perfectly horizontal. One of my directions is actually pointing in the ramp direction. So I'm going to call this ramp. And the other direction is not y. Y is vertically straight upwards. This direction here is no longer vertically straight upwards. It's kind of up on an angle. But it is perpendicular. Oh, that's kind of overlapping with my arrow there. Perpendicular to the ramp. So they're not necessarily concise names like x and y. X and y are very concise and easy to say, but they're names nonetheless. I've labeled my axes nonetheless. So one direction is going to be the ramp, parallel to the ramp, and the other direction is perpendicular to the ramp. And again, I can draw my acceleration vector. My acceleration vector looks like this. Same as before. You'll notice the same blue line looks the same in box 1 as it, or scenario 1 as it does scenario 2. So just because I've changed my mathematical coordinate system doesn't mean the physical vector in real life is any different, right? However, what does change is my mathematical representation of the vector, right? The vector is what the vector is. It'll point in whatever direction it is inherently pointing in real life. But when I break it down into components, that's what I mean by representation of the vector. When I break it down into components, the mathematical representation will change. So here, just like before, I am going to write a sub ramp and a sub perpendicular to ramp. So we've got two components to calculate. And how much of the a vector is pointing perpendicular to the ramp? How much of the a vector is pointing in that direction there that I circled in blue? And that answer, oops, I wrote it in the wrong spot. That answer is 0. You can see from drawing your picture that no part of the blue acceleration vector is in any way pointing perpendicular to the ramp. So 0 acceleration is perpendicular to the ramp. And what's the component parallel to the ramp? All of it. That entire vector is parallel to the axis ramp. And let me circle this in black. So this is the final answer for the second part using a different coordinate system. And you can see here that the mathematical representation of these vectors are different. And they're different because we've chosen a different frame of reference. We've chosen a different coordinate system. But you can see on the diagram that the a vectors are the same. They're identical. So the vectors themselves are the same, but the representation of the vector is different. So that's kind of where we're going with this. So we got to loop back to this whole notion. We can't lose sight of where we're trying to go here. We're trying to take our blood, sweat, and tears that we put into for the one-dimensional analysis, and we're trying to see, can we use this in expanding to 2 dimensions? So that's where we're trying to go, and that's what I kind of iterated here. Our goal is, yes, we know how to analyze one-dimensional motion, sort of. We had to assume it was a constant acceleration in order to analyze it. But now we're stuck with trying to solve things in 2 dimensions. Do we have to overhaul our approach? Do we have to scrap it completely and start from scratch? You know, is there a way to adapt it? So the answer is definitively yes, we can definitely adapt it very easily. And I briefly mentioned this yesterday. You can see now from the example we just did with the boxes on the ramp, if we take a standard Cartesian coordinate system like x and y, our vectors can be relatively easy decomposed into x directional vectors components and then y directional vector components. And let's say you had a velocity vector. Well, then the velocity vector in the x direction can be easily broken down by v cos theta, just like we did with the acceleration was a cos theta. If you want the y direction, it could be speed sine theta, or I guess in the boxes example, a acceleration sine theta. And as you know, if you have the 2 individual components, it just forms a right angle triangle. So to find the full magnitude of the speed, you just use Pythagorean theorem. Now, I just want to kind of mention here, the little note I have in red, this is all assuming our coordinate system is perpendicular to one another, meaning x is perpendicular to y, or another word I can use for that is orthogonal. Even when I use my other coordinate system, the quote-unquote rotated coordinate system, the ramp and perpendicular to the ramp, you know, the ramp is up on a slant, perpendicular to the ramp, even though it's rotated and it's not quite x and y, there's still a 90-degree angle between ramp and perpendicular to ramp. So the key here is, you can pick whatever coordinate system you want as long as the axes you choose have 90-degree angles to one another. Then you're golden. Because then when you do, for instance, when you do Vx and you do Vy, then it is in fact a simple Pythagorean theorem to get your total V. If we didn't have an axis that were 90 degrees to one another, let me do this in a different color. Let's say we didn't have x and y to be perpendicular. What if we had an axis like this? I'll say v sub a, and here, well, maybe like this, v sub b, and those are the 2 directions of my coordinate system that I chose. Then when I add them, v total, you see that we can't necessarily use Pythagorean theorem because this angle is larger than 90 degrees. So reconstructing everything, it's not mathematically impossible, it's just cumbersome. Like you'd have to use cosine law to reconstruct them. And that's just more work than what's, you know, why make it harder for yourself, right? Keep things simple. Okay, so this is kind of what leads us into the notion of independence. So we're able to write the equations in terms of the components, right? We know that, I've shown you an example of that. And I'm really trying to hit home, why does writing it in components help us to analyze 2-dimensional motion? And you know, here, the component analysis alone isn't the one responsible. As I mentioned, it's the orthogonality. So the answer to this hint here is orthogonality. Or another way to say that is everything has to be 90 degrees to each other. That's really the answer. Now, if you're still trying to wonder and wrap your head around, you know, I don't understand, you know, what would a coordinate system that doesn't have 90-degree angles look like? Let me show you an example. So right here, this is what I mean by independence. A standard XY coordinate system looks like what we have here on the left. Standard XY, right? You know, your Y is vertical, your X is horizontal, and there's a 90-degree angle there. So that means if you step in the X direction, then every step along the X direction is purely only in the X direction. There is no part of that step in the X direction that also takes you a little bit in the Y direction. And same thing with Y. If you step in the Y direction, as you're moving along Y, as you're moving vertically upwards, you are not simultaneously partially moving forwards, right? If you take a different example to that, here you still have X being horizontal, but what if you take your, well, it's not vertical anymore, but what if you take your Y-axis and your Y-axis is not perfectly vertical? Let's say your Y-axis is tilted just a little bit. Why you would invent a coordinate system like this is beyond me. It would be a nightmare to do analysis with, but it's an example nonetheless to show you why this isn't going to work. Now here, if you step along the x-axis, yes, you are moving along the x-axis, that's true, but if you look at the y component isn't totally vertically upwards, right? As you move along the y direction, you're moving partially up and also partially in the x direction, right? So here it says that, this time, a step in the y direction is also partially a step in the x direction. So they're dependent on each other. A step in y partially depends on your position in the x direction as well. So it's not mathematically impossible to perform two-dimensional analysis using this bent coordinate system or this non-orthogonal coordinate system. It's just really, really cumbersome because you've got to be very careful to, make sure everything is neat and tidy and everything's accounted for. Literally no textbook ever shows you any alternatives than just orthogonal coordinate systems, because we have this very nice easy way to extend our analysis from one dimension into multiple dimensions, 2 or 3 or 4 or 5 dimensions, just by keeping everything orthogonal. One dimension, okay, x, positive x, negative x. 2 dimensions, positive y, negative y. 3 dimensions, add positive z, negative z. Right? We have this ability to just keep adding orthogonal dimensions, 90-degree dimensions, and that makes our analysis so much easier. We know sine, we know cos from grade 10 math, we know the Pythagorean theorem from grade 10 math, right? Why would we introduce more complicated math when we don't need to? We can just use grade 10 math to represent all of our analysis. So that's what this summary slide here shows, is that when I say independence in a coordinate system, I really am talking about orthogonality. That's really what that's saying there. Okay, so when do we choose a coordinate system with a 90-degree axis? We can see that the motion in each direction is completely independent. Yeah, I've already said that. So that leads us to projectile motion. And this little screen grab here on the projectile motion slide is exactly the same frame that I have in the typed lecture notes. And there's a reason I put this slide here, because it really it hits home the meat and potatoes of what we're doing. So I'm just going to show you a quick video of something, and I'll show you first, and then I'll explain it, and then I'll show you again. It's a pretty quick video, so hopefully it doesn't eat up too much of our time. I have to figure out, let's see here. Okay. that was a video on projectile motion, and it illustrates what I was showing you. What I was showing you on this lecture slide here. So they had one ball that was dropped straight down, and that represents this red ball right here, right? It just dropped straight down. Its initial speed has two components to it. It has an initial speed in the y direction, and it has an initial speed in the x direction. In this case, it's 0 for both. When it's right when the pin is pulled, it starts with an initial y velocity of 0, meaning initially it's not moving up or down. And it has an initial x velocity of 0, meaning initially it's not moving left or right at all. And then it's subject to gravity, so it has an acceleration, so the velocity changes from 0 to negative to more negative to more negative, and it gets faster and faster negative, and it goes down. Now, the other ball, the yellow ball over here, that was the one that was launched in one direction. So it still has the same initial y velocity. It has a 0 initial y velocity, just like the red ball. However, it has a non-zero x velocity to start with, right? We have that piston that comes out and like strikes the ball, and then it launches it to the right. But when it hits the ball, it only hits it horizontally. It doesn't hit it down in any way. And you saw in the video that although one traveled farther, it actually hit the ground at the same time. And that's really the true heart illustration of what independence means. It means the x direction and the y direction are completely independent from one another. A step in the x direction does not overlap with a step at all in the y direction. So if you want to adjust or modify the x direction, go nuts. It does not impact the y direction at all. So that's really the heart of what we're doing here. We're saying you can take two-dimensional analysis and simply analyze multiple one-dimensional analyses. So if we have a two-dimensional problem, you just do two separate one-dimensional analysis. We did one-dimensional analysis yesterday. You know, it's relatively new to you, I get that. And some of you may not have taken physics before, so you'll need to do more homework and more practice, perhaps, compared to other students. But, you know, it's hopefully eventually when you do enough practice, you'll get the feeling that one-dimensional motion is not that hard. So that's really the beauty of two-dimensional motion, is it's no different. It's one-dimensional motion twice. And it's because of this independence. So now that I've kind of explained it, I'm going to show you the video one more time, and you know, see if you can wrap your head around the fact that a perturbation just means like a change in the x direction does not affect the y direction. So because both balls, both the red ball and the yellow ball, the red ball and the yellow ball, have the exact same y variables, meaning they've got the same gravity, it's g, they've got the same initial conditions, v1y is 0 in both cases, then even if we modify the x direction, the y direction is unaffected. So I'm going to show you that video one more time and see if you can spot what I was talking about. All right, so now you saw that twice. Hopefully it makes a little more sense what I taught when I'm saying things are independent from one another. And you know, that's why we use orthogonal coordinate systems. Now, let's keep going into our talks for projectile motion. I have a poll question here as well. So hopefully we've kind of figured out how to use poll questions. I'm hoping we're all becoming a little bit more smooth with this, maybe using a different device to continue looking at the slide while the poll is up, if it in fact impedes your view. So I'm going to start the poll. Let's see here, poll, launch poll, there we go. So I'll read the question for you. A small cart is rolling at a constant velocity on a flat track. It fires a ball straight up into the air, as it moves. After it is fired, what happens to the ball? A, it depends on how fast the cart is moving. B, it falls behind the cart. C, it falls in front of the cart. D, it falls right back into the cart. Or E, as soon as the ball is fired, it remains at rest. So we have about 70 people who have responded. The responses are actually very interesting. I'm very intrigued by the response. About 96 of us have responded. I think there's about 115 people who are attending. Okay, we have about 100 people. I don't see the number increasing very much. So for the sake of time, I think I'm going to end the poll. If you haven't got a chance to vote, it's okay. There'll be other ones throughout the lecture. So let me share the results with you. I think they're very interesting. B has 43%, technically the winner, but only by a small margin. D also has a fairly substantial number of votes. It's got 42% of you. So there's really not a big difference between 43% and 42%. I'd say that's pretty much a tie. So you have something moving, like a cart that's moving, and you launch a ball straight upwards from the moving cart while the cart moves forward. And the question says, what happens to the ball? Does the ball land behind the cart? Does the ball land in front of the cart? Or does the ball land back in the cart or something else entirely? So B says it falls behind the cart. So B, for those of you who voted B, you're saying, if the cart's moving forward and the ball got launched straight up, the cart would continue moving forward and the ball would come down behind the cart. That's what B says. And D says it falls right back into the cart. So D says when the cart is moving forward, the ball goes up and comes down and lands right in the cart again. Now, if we look at this, I'm going to stop sharing the results for a second. If we think of this using physics, what we just talked about, let's look at the initial conditions. We're talking about the cart moving forwards, so let's call that the x direction, and we're talking about the ball being launched upwards, so that's obviously the y direction. So we acknowledge that the x direction is perpendicular to the y direction, so it's 90 degrees. So we can change something in the y direction and it won't impact the x direction, and vice versa. We can change the x direction and it won't impact the y direction. So what's happening here is the car has an initial x velocity, right? Let's call that Vx. And the ball initially is in the car, moving with the car. So the ball also has the exact same initial x velocity as the cart. So they're moving forward together. And the ball is then given a kick upwards. It's given a kick in the y direction. Well, the y direction is independent of the x direction. So any change in the y direction for one object compared to the other object will not change the analysis of the x direction. Now, when the ball is kicked upwards, it still has that x component of the velocity. So as it's kicked upwards, it's actually still moving forward with the same speed that it was before it was kicked. It's still moving forward at the same speed the cart was moving forward at. There's nothing slowing it down or making it speed up. So that means if you perform this analysis, I alluded to this earlier, if you want to analyze its motion, you break it down into two separate one-dimensional analyses. You can analyze the x direction separately, and you can analyze the y direction separately. And the x direction analysis has the same set of variables for the cart as well as for the ball. Therefore, they're going to travel in the x direction forward at the same speed as each other. So the answer is going to be D. It falls right back into the cart. And there's a little picture down there to illustrate kind of how you might picture this. If you were inside the car, picture, I mean, I'm sure you've all been in some sort of traveling object, whether it be an airplane or a car or something like that. If you're sitting in a car and you toss an object kind of up a little bit, maybe not so hard that it hits the roof, but let's say you're sitting here and you just kind of toss it up and then you catch it in your hand again. When you toss it up, does the object fly backwards and hit you in the face? No. When you toss it upwards, it just kind of comes up and down again. You don't even notice that the car is moving. That is what the first diagram there illustrates. If you're viewed in the car or in the train or in the airplane and you toss something up, to you sitting inside the car, it just looks like it's coming up and coming down again in your hand. But if you are spectating from outside, so if I'm standing on the side of the road and I see a car going by and I see someone throw something up and come back down, to me it looks like that object is traveling along a parabola. But the car is also moving forward, so the car is catching the object. So there is that sort of difference in frame of reference, which is what I was alluding to earlier. That's why we started our conversation with frames of reference. Okay, so let's do this example. We've talked enough about independence and kind of the the structure of the analysis. So now it's time to actually do something with this. So a diver running 2.5 meters per second dives out horizontally from the edge of a vertical cliff and 3 seconds later reaches the water below. How high was the cliff and how far from its base did the diver hit the water? Now, I don't know, you might be a lot like me. When I read physics questions for the first time, it's just a jumble. It's just a mess of words. I don't know. I find that most scientists are not great with words. We're not Donald Trump. Donald Trump claims he's got the best words. I certainly am not bold enough to claim that. So when I read something, to me in my head, it's a big mess. It's a big jumble. So I would recommend reading it once just to sort of get a sense of the context. I know there's a diver. I know there's a cliff. There's something about some water. Read it once. And then read it a second time, but only look for values, numerical values. So here, I don't care if it's a diver or a cowboy or a ball, who cares? Running, okay, running at 2.5 meters per second horizontally. So that means V in the x direction is 2.5 meters per second. Okay, and the edge of the cliff, 3 seconds later, so that means t equals 3 seconds, reaches the water below. How high is the cliff? H equals question mark. And how far from the base? How far from the base? This is going to be, you can call it delta dx if you want. That's totally acceptable. Or if you want, you can call it the range, capital R. It's up to you, whatever floats your boat. Okay, so I've taken all the words out of the problem and I've transformed the words into numbers, which is a very useful thing to do when you're approaching physics problems. Another useful thing to do is I think I would probably draw a picture. So I'm going to draw very badly, I might add. I am going to draw a very bad stick figure of a diver running at speed Vx and jumping and hitting some water below. Now, I don't know, maybe this cliff diver is in, maybe the cliff diver is in Florida and there is an alligator there waiting for him, I don't know. And the trajectory of this cliff diver is going to look something like that. Maybe he lands in the mouth or maybe he lands on the crocodile. I don't know. Okay, so we are asked for, in my diagram, let's label. Let's label height. That's what we're asked for. And we are also wanting to know the range. That's what we're asked for. So I can't say this strongly enough. When you're analyzing multiple dimensions of motion, whether it be only 2 dimensions like this question or 3 dimensions, we just break it down into multiple one-dimensional analysis. So we have X and Y, those are independent from one another. So we just perform 2 independent analyses, one analysis in the X direction, one analysis in the Y direction. So let's do that now. Let's say X and Y. I'm going to make a chart. If you have a physics training from high school and you have your own way of doing it, that's okay too. I'm just going to use a chart to help keep, to help organize your thoughts. If you have a different way of doing it, that's totally fine. So I'm going to go through, and we know that we have a certain set of variables. I think we have 5 variables-ish to write or to analyze in each dimension. And let's see what we have and what we need for X and Y. So we have speed in the X direction, acceleration in the X direction, delta D in the X direction. We have time in the X direction. And then we've got pretty much the same set of things for Y. We have V initial in the Y direction, V final in the Y direction. We have delta D in the Y direction and time in the, X and Y, there we go. So V in the X direction, we're told that this guy is running horizontally at what, 2.5 meters per second. So we can say 2.5. Acceleration in the X direction. Well, that's going to be 0 because gravity pulls downwards. Now, just so we're clear, I put a cross through my zeros just to make it clear it's like a 0 and not like a badly written E or a badly written like O for something like it's 0 cross, just to denote that. Delta dx, that's what we're asked for. We're asked for range. So we don't know what that is, so I'm just going to call that R. And time in the X direction. Well, we weren't given time in the X direction, but I do know that time in the X direction is actually the same amount of time spent in the Y direction. So I'm just going to call that T. And V initial in the Y direction is 0. This thing does not start with a, or this thing, sorry, the diver, they're a person. They start with an initial speed in the Y direction of 0. Even though that's not explicitly written in the question, you can tell from context that they jump off horizontally. So it's just like that ball in that video I showed you. It gets an initial shot out horizontally. It's not shot upwards, it's not shot downwards, it's shot out horizontally. V final, I don't know what V final is. I don't even know if we need to calculate it, but I'm just gonna put question mark for now. And we're asked for height. Delta dy would be the height of the cliff. So this is me breaking it down, breaking the information down into separate components. So there you go, separate components. Now we have to perform two independent one-dimensional kinematic analyses. So we studied one-dimensional kinematics yesterday. So we can do that now. Let's start with the y direction. We know that delta dy equals v1y plus 1/2 a t squared. Sorry, we know t. Sorry, we know t. T is 3 seconds. There we go. And this is v1y, there we go. And plugging everything in, we know delta d in the y direction is actually the height. v1 in the y direction is actually 0, as we specified in our table over there. So 0 plus 1/2. Oh, I forgot a. That's what I forgot. Oops. Let's see here. Let me move. Let me move this down. I forgot to write a. That was my bad. So the acceleration in the y direction is going to equal gravity, g. Okay, so back to black. So a is going to equal g t squared. So my height is simply gt squared over 2, which is going to be 9.8 over 2 times 9. Time is 3, 3 squared is 9. So if you want to calculate this precisely, go nuts. If you had a calculator with you, go nuts. I am going to use the estimation ideas that we used previously and say 9.8, that's pretty close to 10. 10 divided by 2 is 5. So 5 times 9 is around 45 meters. So the real answer isn't 45, but the real answer should be approximately 45. We'll check what the real answer is momentarily. So that's one of my two independent 1D analyses. I need to now do my second one-dimensional analysis. We want to know the range. Well, the range is going to be the acceleration in the x direction is 0. So if we look back at our one-dimensional kinematics equations, which equation does not have an a in it? Well, if we look back, the one that does not have an a in it is going to be v equals d over t. That's when acceleration is equal to 0. So here, I'm asked for d, so this is going to be dx vx. So dx, which is actually my range, is going to be vx times time. And my vx is going to be, what did I say? It was 2.5. And time was 3. So 2.5 times 3. Again, if you had a calculator, go nuts. If you want to use your estimation principles, you would round 2.5 probably down to 2, because 2 is an even number, or you could round it up to 3. So you know the answer is going to be somewhere between 6 and 9. In fact, I think it's going to be 7.5. I think it's going to be, or 8.5. Wow, anyway, it's going to be smack in the middle of those. So we estimated without a calculator the answer for height to be 45 meters and the range to be smack in the middle between 6 and 9. So the real answer, yeah, it was 7.5. That's what it was. So the real answer is 44, which is really close to 45. And the real answer for range is 7.5 meters. So you can either estimate it using, you know, the estimation rules, or, you know, if you have a calculator, you can go nuts with the calculator. Okay, before we do the next example, I'm just going to open the chat window momentarily. I know Brandon's been hard at work. I am just going to take a look at the chat here. If you have any specific questions, you know, you can type them now, and I'll see if I can address them. Oh, now that I look at the chat, it's just blank. No one's asking anything. Okay. Did we already cover the material related to question 3 in assignment 1? Well, that's not really a question relating to this. So I'll answer that one later, because right now we're in the middle of talking about projectile motion. Okay, so it doesn't look like there's any specific questions. So I think I'm with everybody, and I think you're with me, hopefully. So let's keep going. I have another example that we can do together. A football is kicked at ground level with a speed of 18 meters per second at an angle of 31 degrees to the horizontal. How much later does it hit the ground? Again, I do not like words. When I read a word problem, it gets all jumbly and I just get confused. So, you know, reading it once, I know there's something about a football and, you know, someone's kicking a ball, okay? Second read through, ignore the words, only write the numbers that you see. So here I see the initial speed of 18 with an angle, okay? So I know my initial speed is 18 meters per second at an angle of 31 degrees to the horizontal. I'll draw a diagram later to make this more concrete. And then we want to know how much later does this hit the ground. All right. We don't have a lot of explicit information, but you can go back and you can draw your chart. So X and Y. So I say Vx, AX, delta dx, and time. And over here we have Vy, AY, delta dy, and T. T. So Vx, well, we know if this is my ball, we know the velocity is up on an angle of 31 degrees. So that means my initial speed in the x direction is going to be v cos theta. Notice how I'm not plugging in numbers. Notice how I'm not typing in like 18 times cos 31. Try to keep everything as a formula as much as possible. I strongly, strongly, strongly recommend that. The acceleration in the x direction is going to be 0. Delta d in the x direction is just going to be the range. We don't know what that is. They may not even be asking for it, but it's definitely not given in the question. And t, time, is also not given in the question. And Vy is, if you look at our picture here, it's going to be V sine theta. The acceleration is going to be 9.8 meters per second squared. And delta dy, delta dy. Well, this one's a little bit tricky. It's not explicitly mentioned. The value of delta dy is not explicitly mentioned in the question, but you can infer it from context. The ball is kicked, and it says it lands on the ground. So the ball starts at a height of 0, and it lands at a height of 0. So what's the displacement in the y direction? I 100% agree with you that there is a non-zero displacement in the x direction, right? It clearly moves forward. But what's the change in altitude before versus after? And you'll notice here that it starts off at ground level and it finishes at ground level. So this means that delta dy is in fact equal to 0. And time again is still time. Now, looking here, we're actually asked to solve for time. So I can perform two different analyses. We can actually solve for range as well. The question doesn't ask us for range, so maybe perhaps we will not waste time solving for range, but it certainly asks us for time. So we at least have to solve for time. So when you're doing these calculations, you can keep the two variables separate. You can keep the x variables separate from the y variables and do two separate analyses. So I'm looking here, is there a way to solve for time using the x direction? Well, I am missing 2 out of the 5 variables. I'm missing delta dx, I'm missing range, and I'm missing time, but I do have, 4 variables, but I do have acceleration and speed. So I've got 2 out of the 4 variables there. That's not enough information to solve for what I need to solve for. If I look for the y direction, I have initial speed, I have initial, acceleration, and I have the displacement in the y direction. I have 3 variables and only 1 unknown. So if you have 3 variables and 1 unknown, that is enough information to solve. So the equation we'll need here, if you look at our 4 really, I guess there's technically 5, but we don't really care about that last one. So if you look at our 4 kinematics equations, which equation would have speed, specifically initial speed, v initial speed, acceleration, delta dy, or I guess delta d, and time, v1, a, d, and t. So if you look at your list of 4 equations, then you're going to see we have delta d equals v1t plus, I'm still in this mode, delta d equals v1t plus 1/2 a t squared. And we are doing this analysis in the y direction, so everything here has a subscript of y, y, y. Time doesn't get a subscript because it's the same time in both the x and the y. And now I'm going to remind you here that we technically are dealing with vectors. Technically everything here, other than time, is a vector. So we need a coordinate system for a vector. I don't care whether we make up or down positive. Just for the sake of logic, I think, let's make up positive. So if up is positive, when I take off my vector signs, if the quantity in the question represents upwards, it's going to remain positive. If the quantity in the question represents downwards, it's going to become negative. So delta dy is in fact 0. So there is no positive or negative question there. v1y, the initial velocity in the y direction, the ball was kicked upwards. I mean, you can't kick a ball into the ground unless you're maybe the Hulk or something, but barring that, you're kicking the ball upwards. So this is going to be positive v1y times t. And acceleration in the y direction. Well, acceleration is downwards, so we're going to make this negative. And a sub y is simply g, and then t squared. And I think we have everything we need. We have v1y, we have g, and there's only one variable, it's time. So one equation, one unknown, we're good to go. So let's just use our math skills here. Keep plugging away. v1y is actually going to be v sine theta minus gt squared over 2. Oh, I forgot a t equals 0. And because the left-hand side equals 0, we can actually cancel one of the t's. So well, technically you're dividing both sides by t, but 0 divided by t is simply 0. So v sine theta minus gt over 2. So this tells me that t is in fact going to equal 2v sine theta over g. So there's your answer. 2v sine theta over g. Now, I've been mentioning this a few times. It is good to keep your answer throughout the entire process as variables as much as humanly possible. It's pretty easy to not plug in numbers here. It's pretty easy to keep things as variables, so I would strongly recommend keeping everything as variables as much as possible. So that's what I've done here. If you happen to have a calculator nearby, you can start plugging in values if you'd like. So this is going to be 2, what was my speed? 18. 2 times 18 times sine of 31, I think. Was it 31? Yeah, 31 over 9.8. By all means, if you had a calculator, crunch those numbers to like 1 or 2 decimal places, whatever floats your boat, right? However, I don't have a calculator. So let's do some approximating, shall we? And then maybe we can compare our answer, our approximated answer, with the mathematically calculator answer to see how close we are. 2 can stay as 2. 18 can be approximated as 20. 9.8 is close enough to 10. Sine of 31, oh boy. Well, I don't know what sine of 31 is, but what are some of the special angles that we know from high school? We know sine of 30. And I think 30 is pretty close to 31. So sine of 30 is actually a half. So I'm going to approximate this, not sine of 31, I'm actually going to approximate this as the sine of 30. And then going through with this calculation, oh, that's blue, sorry. 2's cancel, 10 and 20 cancel, so you actually get 2 seconds. So this ball, is it a ball? Yeah, this football is only going to be in the air for approximately 2 seconds. Now, in real life, it might be more like 2.1 or something like that, because I was doing some approximating, but it's going to be around 2 seconds. And the real answer, if you plug everything in, is in fact 1.9 seconds or 1.89 seconds. So that's pretty close to 2. So seeing as how I didn't have a calculator, you know, this estimation stuff has some merit to it. Okay, we have a few more worked problems to do. I'm just looking ahead here. Yeah, we're pretty much almost done. What I'm going to do is, I'm going to do something radical. Zoom has this ability to break you guys out into independent, smaller groups. So I want to see how well you guys work on one of these problems on your own, just to get your hands dirty during the lecture. And once we're done this, I think we're going to spend the rest of the time going back in the previous chapters and doing some of the examples we didn't have time for. But before we do, I think I'm gonna break you guys out into smaller groups randomly. I don't know if Zoom is going to do it randomly. And you know, you're going to be able to, I believe you can unmute yourself. You can, you know, show your video if you want to. There's a way to share a whiteboard, I believe. So if you know, try to work on this problem. Give it some time. I might give you five or 6 minutes or so, maybe a little bit longer, maybe 10 minutes to work on it. And then I'm going to bring everybody back together and review the problem with you that way. Okay, so for those of you watching on YouTube at a later time, I'm going to stop the recording now because I don't know how the recording is going to handle the breakout sessions. So I'm going to stop the recording now, and you know, because you know, and we'll resume it later. Okay, there we go. All right, so now we're recording again. We've ended the breakout session. If you're watching on YouTube, you haven't missed much. We've just ended the breakout sessions, and we're going to take up the question that we were assigned to do before the breakout session. Okay, so we read the problem. There's a lot of words. It gets a little bit confusing. So we read the problem a second time, writing down the givens, and then hopefully that makes things a little bit easier. So a rescue plan, that's my typo, should say plane, drops supplies to isolated mountain climbers on a rocky ridge. There you go, 235 meters below. So delta dy is 235 meters below. Below meaning down, down meaning y. So it's in the y direction. If the plane is traveling, the keyword there is horizontally with a speed of 69.4. So horizontally means x. This is going to be 69.4 meters per second. They want to know how far in advance. Oops. How far in advance. So that's going to be delta dx, or another way to say it is the range. How far in advance should we drop the goods so it lands at the proper location? Now, just to make sure we're all on the same page here, physics is both intuitive and unintuitive at times. If you're flying a plane, you might think if the plane is here, directly over top of the mountain climbers, while the plane is traveling forward, you might be tempted to look straight down and say, oh, they're directly below me right now, meaning I should drop my cargo right now. But if you drop your cargo when you're directly over top, the cargo also has a forward velocity. So the cargo would actually land over here, which would be a problem. So you can't drop your cargo when you're right on top of the people. You have to drop your cargo before you're on top of the people, because when you drop your cargo here, the cargo will follow a parabolic trajectory because of that initial speed in the x direction. So that's kind of the physics concept here. You have to drop it beforehand. Okay, so we've listed our givens. I would say normally we draw a picture, but the picture is kind of provided to us in the question, so that saves us the effort. We can now go through and write the chart. Now again, if you don't like the chart, you don't have to use the chart. We use whatever method you need to use to get the correct answer, but I'll show you the chart because I think it's a good way to organize yourself. So x, y, and so x we have, let's see here, we have vx, delta dx, ax, and time. All right, and then in y we have vy, delta dy, ay, and time. So time is the thing that connects the two dimensions together because it's the same time in the x direction as the y direction. So that's the thing that we're going to need to bind these two together. But everything else, if it's a vector, it's going to have different quantities in x and y. So let's look at our givens. I'm not reading the question again. I'm just looking up at my givens. What am I given? I'm given delta dy. So I'm given this is 235. I'm given Vx is 69.4. I'm asked to solve for the range. Although we're not explicitly told this in the question, we can tell from inferring it. The plane is traveling horizontally. So the velocity in the y direction is 0, at least initially. After you drop the cargo, obviously it'll gain some speed in the y direction. The acceleration in the y direction, again, it's not explicitly said in the question, but again, you can infer it. It's gravity. So it falls with an acceleration of 9.8, or little g is the symbol. And I don't know why the pen is wiggly near the bottom. I Googled that, and apparently it's a known problem with the surface. Anyway, so there you go. We've listed all of our givens, and we don't know time. So we ask ourselves, can we solve for what we need? We need the range, right? We need the range. So if you have little practice in physics, I would recommend trying, your first step should be trying to come up with an equation that includes the quantity that we need. And it may not be the final equation, but it'll help guide your thinking. So here, I know we're asked for range. So range shows up in the x direction. So I'm thinking to myself, okay, a is 0. We don't have time, but we're probably going to need time. So a is 0, d, v, and t. What equation do we use? Now let me change colors here. So we would probably use vx equals dx over t. And I make note of the fact that we have vx. We're asked for d, but t is also unknown. But we're asked for d, so we should probably rearrange for d. And hopefully we can solve for time another way. But the fact that we're asked for the range, dx, tells me we should probably isolate for dx on the left and have everything else on the right-hand side. So this tells me we have this, but we're looking for the time. We don't know the time. That's a terrible question mark. There we go. We're looking for the time. Now, if we need another variable, which we do, we look to the other dimension, our independent other dimension y. So here we have the same time as we do in x. So if we isolate, if we come up with some equation for t or that has t in it with a y equation, we can rearrange and say t equals and then plug that into our other equation. So that helps, starting with this, even though we don't have time, starting with this equation helps us guide our analysis. So we go now to the y direction. And we say, okay, we have v initial y is 0. So v initial y, delta dy, a, and t. What kinematics equation has v initial y, d, a, and t? And that would be, what color am I using? Red. Let's go back to black. So that would be delta dy equals v1t plus 1/2 a t squared. And I guess I should say y. Vector, vector, vector. All right. Now, technically, these are vectors, so we can say, let's say let up be positive if you want. So delta dy, this package is falling. Falling means down. So if we let up be positive, then this delta dy is actually going to be negative. So I'm going to drop the vector sign and then add a negative. v1 in the y direction. Well, v1 in the y direction is 0, so that just kind of disappears. 1/2 a. Well, the acceleration of the y direction is down, so I'm going to drop the vector sign and add a negative out front. And a is equal to g, and then t is just t, or I guess t squared. So do we have delta dy? Yes, we do. Do we have g? Yes, we do. And we don't know time. So that's it. We've got one equation, one unknown. We can absolutely solve for time. So let's do that now. T equals the square root. You'll also notice that the two negatives cancel out, which is helpful. 2 delta dy over g. And what we do is we can take this equation and we can plug it in to our other equation. So finally, we say delta dx equals vx times t, which is going to be vx times the square root of 2 delta dy over g. And this is your final equation. They've asked you for how far in advance, which means the range. Do you need to drop the package? So there you go. That's how far in advance that we need to drop the package. I've mentioned this a few times. I strongly recommend on all of your assignments, all of your tests, on the exam, please write a final derived equation, and then in your last line or two, plug in values and then use a calculator. This is there's two reasons for this. One you're not going to like, and one you hopefully will like. The first one you won't like is it helps you practice, get good with math, become comfortable with equations. and it actually provides a lot of insight into how the variables relate to each other. Like looking at this here, I say, you know, if the plane is going twice as fast, by how much do I have to compensate the horizontal, the drop distance? You say, well, okay, look at the equation. If Vx goes up by 2, dx goes up by 2. You can say, well, what if I fly lower? You know, like what if it's safe to get the plane a little bit lower? Well, if you reduce your height by a factor of 2, how does that change your horizontal drop distance? It's not a factor of a half, it's a factor of root 2, like 1 over root 2, because the delta dy is underneath the square root sign. So having the final derived equation helps you see some insight into the variables. So that's the one you won't like. That's the reason you won't like. But trust me, the more you practice, it will become helpful. The second reason you should do this, and this is the reason you should like, it helps us give you part marks. It's very rare that, you know, students in physics are just perfect with everything they do. I mean, I'm not even perfect with everything I do. So if there is something wrong on a test, it is really, really easy for us to award you as many possible part marks when you keep everything as a variable and only plug in at the end. Because if you just made a stupid, silly mistake, like a plus should have been a minus, then it's easy for us to spot if everything stays as a formula. And then we're like, oh yeah, that plus minus, that's just like a 0.5 out of 10, you know, no problem. That's a very small thing. But if you plug in numbers here, and, you know, like numbers combine to get more numbers, and you get the wrong final answer, we don't know if it's because that's a small mistake or if it's a big mistake. So it's really hard for us to give you part marks if you plug in numbers halfway through. So please, 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 please try to get your final equations as much as humanly possible. Now, again, just to practice, because I know we didn't do a lot of estimation examples in lecture, so I'm trying to sort of incorporate them as we do some of these questions here. So I don't have a calculator with me. I hate calculators, by the way. You'll almost never see me use a calculator. So let's just see if I can ballpark kind of what this is going to be. Vx, what was Vx? It was 69.4. Okay, so let's approximate this to 70, because 69.4, who cares? Square root of 2 delta dy. What was delta dy? 235. Let's pretend it's 200. Over g. G is around 10. Okay, so cross off one of the zeros. So 2 times 20 is 40. So this is going to be around 70 times root 40. Root 40 obviously is not a perfect square. The closest perfect square to 40, I think, is 36. So root 36 is 6. So this is going to be approximately 70 times 6, approximately. And then 7 times 6 is 42 with a 0. Is 420 meters. So the answer is approximately 420 meters. Again, I'm not using a calculator. These are just using some sort of ballpark estimation techniques. So let's just scroll down just to see what the real answer is. Did they ask? Oh, okay. And then here, so it looks like the real answer is 481. Without a calculator, I got 420. So I'd say that's a pretty good estimation. And I want to remind you guys, because I've been getting a lot of emails about this for assignment 1. There's no hard and fast rule necessarily about order of magnitude calculations. I'm trying to emulate or mimic for you kind of how to do those when I do these sort of estimation numbers here, when I do these work examples. We know it's not the correct answer, so it's okay. You know, whether you round 2.5 up to 3 or 2.5 down to 2. You know, it's okay. Just pick one. You know, we know it's not going to be the mathematically correct answer. The point is it's an approximation. So, you know, not having used a calculator, 420, I think is pretty close to 481. So there you go. The other thing I want to mention about assignment 1, question 2 is a little bit different. Question 2 has you guys making some reasonable assumptions about some of the values. In question 1, I think there were some pretty concrete values you could have used, and then you would have had to round the numbers appropriately. But for question 2, you know, it says things like, you know, how much money are you going to have if you put $200 a month away? Well, you know, if you literally just put it in a savings account with no interest, then that's a really easy calculation. It's just 200 times 12 months in a year times 40 years. That's not really much of an assignment question, right? So, you know, why do parents tell you to start investing money when you're 18? You know, why do we start telling you to make a TFSA, a tax-free savings account, when you're 18, or a RRSP, a registered retirement savings account, when you're as young as possible? The reason is because of compound interest. So, you know, I'm not saying to sit there and you know, mathematically calculate rigorously exactly how much money you're going to make, but, you know, make some approximations. Who knows what the interest rate is going to be? The market fluctuates. You know, the coronavirus tanked the stock market, so who knows, you know? But make some reasonable assumptions, you know, assume a certain interest rate. If you do continually compounding interest, yes, that formula is a nightmare. I agree with you, but, you know, approximate it. You don't necessarily have to do continually compounding interest. You can do simple interest, right? Simple interest is reasonably easy to calculate without you know, a huge complicated formula. Like, there's no one correct answer. That's what I'm trying to get at here. There's no one correct answer with these assignment questions. It really is just make some reasonable approximations, and as long as you can justify your choice that makes some sense to somebody, you know, I think it has some validity to it. You know, the example was the New York piano tuners. So please go back to the typed lecture notes with the new how many piano tuners there are in New York. I outlined for you some assumptions we need to make, and yeah, maybe the values I picked are wrong. You know, maybe someone who works for the New York City government, you know, has documents like, oh no, I have this number here. Okay, fine. You know, if you're privy to some fancy information, go nuts. But, you know, if you're just an average Joe Schmo, you know, make some reasonable assumptions, and as long as you can defend your reason, that's literally the whole point. This is literally what it means to be, you know, numerically literate. You know, can you make some reasonable assumptions about some things? You know, one of the questions in the assignment asks you to approximate how much profit the gas companies are making. And, you know, this is particularly relevant because, you know, now that the gas prices are so cheap, you know, they're saying, oh, the oil company needs bailing out. The oil company needs bailing out. Well, do they? Yes, gas used to be $1.30 something, but, you know, now it's 80 something, you know, and they're claiming they need all this help financially, but do they? You know, does that logic make sense? You know, it's like when Donald Trump spews his numbers out of his face and he says like, oh yeah, you know, only this many people have died from the coronavirus. Well, think about it, you know, like there are so many states, and, you know, if you assume, you know, 1,000 people from each state, multiply by, you know, like you can do some reasonable approximations and just to fact check, so, like, the order of magnitude of some of the numbers being presented to you. That's all these questions are supposed to be for, is to just practice your critical thinking, your problem solving, your numeracy skills, because physics is ultimately a very, very number heavy field. You know, yes, there's equations and formulas, but, you know, you have to talk about reasonable numbers. Like, all of this math is rooted in real life. You know, if you calculate on a test that the airplane is going, you know, Mach 6, that's 6 times the speed of sound, there's something wrong there. You know, airplanes don't travel at 6 times the speed of sound. So, you know, I'm just trying to have you guys develop a little bit of intuition with the numbers. And then that way you can sort of fact check the validity of some of the numbers that both you calculate and what people tell you in day-to-day lives. Okay, so it is 1 o'clock. We have completely finished motion. There is a few more examples in these lecture slides. We did not have it, actually there's one more. There's one more example we didn't get to. I strongly recommend, as part of your homework, sitting down and trying to do this last one, the Spy Master Chris flying across a constant, you know, 208 km/h horizontally, blah, 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 blah. Try doing that on your own. As you see here, the solution is right below, so you can always double check your answer. But, you know, please practice trying to derive these equations and, you know, do some sanity checks with your answers. So just to make sure your calculator and you have a good relationship. And as always, you know, just because it's not in the lecture slides in terms of an example problem doesn't mean you're good. You know, you should be, after every lecture, you should go back and open the textbook that you've found and, you know, do some practice problems in the back of the projectile motion or the 2-dimensional kinematics chapter. in whatever book you're using. Honestly, all the books are pretty much the same. So just because you may not have the Giancoli book, but that's okay. I guarantee you the back of the chapter problems are still pretty good. So do as many of them as you need to in order to start feeling confident in your abilities in this chapter. And that'll be different. Some of you will do 2 questions and be like, you know, this is easy, I'm bored. Some of you will do 10 or 20 or 30 before you start realizing that all the questions are the same. But, you know, I can't do everything for you. You can lead a horse to water, you can't make it drink. So it's a 2-way street. Please, please, please be, you know, do some homework as well. I think there's a post-class quiz this week. I believe it's due Thursday, tomorrow at 7 p.m., but please double check that number. I could be misremembering that number, so please double check that. But there is a post-class quiz. It's not overly detailed, and again, if you get something wrong, it's not the end of the world. The post-class quizzes are meant to sort of make sure you're leaving this week with a good understanding of the general ideas that were talked about. So, you know, we talked about measurement and estimation, 1-dimensional motion and 2-dimensional motion. So there's just some simple questions there to make sure that you're sort of, you know, up to par with what we're doing. Okay, see you guys next week. I'm going to stop the recording now, and I'll hang back a little bit for the chat to see if there's any burning questions. But for those of you looking on YouTube at a later time, I will see you guys on Monday. Have a good weekend, guys.